All right, for example 1, we want to graph the relation A, which is a set of 5 points. So let's see, -3, -1, that's going to be 3 places to the left and down 1. And then we have -2, -1, so that's 2 to the left and also down 1. We have 0, 4, so I don't move left or right, but I do go up 4 places. Okay, we have 3, 0, so that's 3 to the right, but we don't go up or down. And then, okay, we get -2 again, and we go up this time to 3. And we're done. This is our relation. Next is, what is the domain and range of this thing? So you could look at every single point and note what each of the x values are and just record those. So I'm going to scroll down a little bit. So I'm going to call my domain D, and I'll use some set notation, but I'm just going to list the x values of each of these points. So starting with the one that was at -3, -1, the corresponding x value is here on the axis, so we get -3. And if I do this for the remaining points, okay, actually for these 2 points here, we get -2. We have for the point here, it's right at 0. And then the last one is over, it's right on the axis, but that's at 3. So here we go. The domain is these 4 values, -3, -2, 0, and 3. For the range, it's really similar. So for the range, I'll call it capital R. I'm just going to use the other axis this time. Okay, so if you look at these 2 points, it corresponds to this y value, which is -1. So I'll write down -1. Okay, we had this point over here, which was at 3, 0, and its y value is over here, so we do get 0. And there's 2 other points remaining. This one has a y value of 3, and the last one right here, it's actually on the axis, but it has a y value of 4. There are no other values in the domain in the range because there's no other points located on our graph. The last question is this relation also a function? And our definition is it true if every x value corresponds to only one y value? So you could go through point by point, like starting with this one here, which is at -3, -1. The x value is -3. It corresponds to y is equal to -1 and nothing else. So nothing goes wrong with this point. But there is a problem if you go to this point here. So I'll write it off to the side. This was the point -2, -1. Well, above that is also the point -2, 3. This is a problem. This relation is not a function. Here you have an x value, which is -2, but it corresponds to 2 y values, -1 and 3. So by our definition of a function, this thing cannot be a function. This is the only x value, which is a problem. The other 2 points are fine. But if it goes wrong once, this thing cannot be a function. For the next example, I'm actually going to draw a graph on here. This will have infinitely many points, so I can't just list them out. I think I'll draw it like this. I'll start here, and I'm going to go up until I get to here. A closed circle means that it's going to contain that point, but an open circle just means at this spot, nothing is there. And then I'm going to go from this point over here. And maybe just to get a couple more things on here, I'll draw a graph going from this spot over to this one. And this is going to be my function, this graph here. There's no equation for it, but it has 3 separate pieces and there's a hole missing at a couple of spots. So first question is, what is the domain of this function? It's harder if you have infinitely many points, but you can really take the same approach. So I'll scroll down a little bit here. I'll start with domain. Now, if you look at this very first segment that I drew on the left, I'll just choose a random spot in here. The corresponding x value for this is located here on the axis. So in trying to determine the domain, I'm just trying to think about what are all the x values for the points that appear on this portion of the graph. All of those x values start at -5 and they go towards -2. So I'll write that down here like this. That's from -5 to -2. And I'll put this open parenthesis here. Now it picks up again when it gets to this spot here. And as we move along this portion of the graph, the x values go from -2 to 0. So here's where I'm going to use a union. Okay, we're going from and including -2 up to 0, but I'm skipping over 0. And then for the last piece, going between those 2 points, let's see, it starts at x is equal to 0, and it goes up to and including 5, and we get a union like this. So this will be the domain for each portion of the graph. If you look at the corresponding x values, they'd have to fall into here. And actually, we can simplify this a little bit. So just to scroll down just a little bit, not too much. All right. You could actually write this domain as going from -5, but all the way to 0, because you have -2. It's not on this portion, but then it does include it here. So this is really just saying you're going from -5 to 0. You're also going from 0 to 5, and I'll put a union between those. So this would be the domain of this relation. If you want to know what the range is, maybe let's go back up a little bit. So this would be the y values. So if you want the range, you can pick any spot on the graph. So maybe, if you pick a spot here or here or here, you're getting these values on the y-axis. So you're going to get everything that goes from 0 up till you get to 3. So we get from 0 to 3. And actually, you are including 3 as well, because every single portion on this spot, on this part of the graph, is actually 3, so you can include it as well. The last thing that happens is at 4, there's a whole portion of the graph over here that corresponds to y equals 4, and that's actually all you get. It's just the point 4. So the union of these two things is the range of this relation. And furthermore, looking at this graph, this is definitely a function. Every x value that you pick in the domain corresponds to only one y value in the range. So like if you're looking at an x value here and you want to find its corresponding y value, it's located up here, but you don't get another one. You just get that one. There's no spot in the domain where you're going to get 2 y values back. So this is a function. So in this course, we are probably going to use equations more than listing out points or drawing a specific graph. So here we have a relation x plus y is equal to 5. It's a formula that relates x's to y's. So what we're going to do is try to find some points that make this true. We'll plot a few of them, and when we get an idea of what the graph looks like, we'll just draw the graph and we'll stop. So we're dealing with x plus y is 5. One approach is just to think of numbers for x and y that make this true. I mean, for example, something that's really easy would be 0 plus 5 is, well, that's definitely 5. And here we're saying 0 is x and 5 is y. So the point 0, 5 makes this relation true. It means that you can graph it. So I'll place it right here. If that one made sense, then another very obvious one would be, well, what if you switch it? I know 5 plus 0 is also 5, and that means x is 5 this time, and now y is 0, and this point makes the relation true. So that's the point located here. Really, once you have enough points so you're satisfied that you know what the equation looks like, you can just draw what you think the equation is going through it. But I just want to get a couple of others on here, maybe taking a slightly different approach. If we want one more value, another obvious choice would be, well, if we did 1 plus 4, I mean, that's definitely equal to 5. And here you're saying x is 1 and y is 4. So that's going over 1 and up 4. So we get a spot here. Again, you could switch this at this point. You could say, well, if it was 4 and 1, you also get 5. So this is the point 4, comma 1, which is located 4 to the right and up 1. And I'm kind of convinced at this point that this is going to be a linear equation. I'm just going to connect all of these points with a line. And this thing's going forever in both directions. Maybe a more familiar approach to use to take the equation x plus y is 5 and solving it for x. In this case, you could subtract x from both sides. It's probably not necessary for this formula, but at least now you could set up a table of values. You could say, all right, I'm going to choose some values for x, find their corresponding y's. It's going to be very organized in this table. So you could do something like -2, -1, 0, 1, and 2. And finding the corresponding y values is just a matter of putting these x's into the formula up here. I won't actually list them out for this problem since I think it was good enough just to pick some points to see if they in fact worked. And they do. We get this relation. And if we want to determine the domain and range for this, we can use the graph that we've just come up with. So I'll put domain and range. This is tricky because there's infinitely many points, but if we choose any spot on this graph and you want to know the corresponding x and y value, you would look over to the y-axis and the x-axis. As this point moves along the graph, you're going to get every single x value back. So like if you chose a spot over here, the corresponding y value is here, and the corresponding x value is here. You're never going to miss anything. You actually get all values back. So the domain is going to be from -infinity to +infinity. And the same is true for the range. It's all real numbers for both. For our last example, example 4, sketch the relation x is equal to -4. And in this expression, there are actually no y. So like, what does that mean in terms of the graph that we get? So here's an example where you can't solve for y and plug in x values because in fact, there is no y to solve for. So you could go back to this approach of just trying to think of points that make this thing true. So again, you're dealing with, all right, you have x is equal to -4. Can you find any points that make this a true expression? So there are a couple of easy ones. I'll start with -4 for x and 0 for y. Is this point true in this relation? Well, any place I see an x, I'm going to put a -4. So I go up to my formula and I say, okay, I'll put -4 in place of x. And any place I see a y, I'll put a 0. Well, there are no y's, so the 0 doesn't go anywhere. And if I complete my equation, I get -4 is equal to -4, which is true. So this point, -4 is 0, works, and I'll place that on the graph. Probably need a few more points to get a picture of this, but I think I see what's happening. If I leave -4 alone, and let's say you put 2 in place of y, I mean, clearly this has to make the relation true as well. -4 would go in place of x. The 2 doesn't go anywhere. You would get -4 is equal to -4, and so you get a point that's located here. You get every single y value back. You have -4, and no matter what you choose for y, it'll make the equation true. So you could have put 5 in place of y, or 10, or -1. And since everything works, try to draw this as best I can here, but it's just going to be a vertical line that was supposed to be vertical going through an x value of -4. So for this particular relation, the domain, it's actually just -4. There's no other x value on this particular graph. However, if you look at the range of this thing, you get every single y value. You get everything from -infinity to +infinity. And really the last thing to consider here is this relation also a function? And clearly this is not a function. This is probably the worst case scenario for something not being a function. You have one x value and it actually goes to infinitely many y values. And since that's more than one, this thing is definitely not a function.